So this is chapter 4, section 6, mean value theorem, and number 33. This one's hard because you have to take that theorem and make it make sense in the context of this problem. So let's read this. You have a state patrol officer, saw a car starting from rest. She radioed ahead to another patrol officer 30 miles further down the road, and the car reached the other officer in 28 minutes later. Okay, so let me draw a graph of that. So this is my time, and this is my, and we'll do in minutes, and this is my position of the car. I'll call it x of t, and that's in miles. So what happens? A car starts at rest, so it's not moving, on a highway, on a ramp. So it starts position 0 at time 0. And then 28 minutes later, so 28 minutes later, the car is 30 miles down the road. So the position here, let's say this is 30 miles, the car is going to end up here. Now, we don't know what that graph of the car looks like. Did it go really fast at first and slow down? Did it go the same speed the whole time? Did it kind of go slow and then speed up? We don't know what the graph looks like, but it doesn't matter. I am going to draw a possible look of the graph. I don't know what it looks like, but this is a possible look of the graph. I don't know. But what's the implication? Well, what it says is the car of the driver was given a ticket for going over 60 miles per hour, even though the police officer here clocked its speed at 60 miles per hour. And the police officer here saw the car take off. So the police officer never saw this car's speed. So how do you give him a speeding ticket based on this information? Well, let me show you how. This is mean value theorem problem. Okay. Again, I don't know the graph looks like this. That was just a guess. It could have been this. It could have been flat. It doesn't matter, and here's why. The mean value theorem says if you have a function that's continuous, now, if a car is traveling down the road, you cannot have a gap in its position, or you can't have a jump in position, because a car doesn't suddenly go from this position to this position in no time at all. So it is continuous. And it is differentiable also because a car's velocity cannot change instantaneously. It's gradual, the change. So you can't be going one speed and then instantaneously change to another speed. You never have a sharp corner. It just can't happen. It has to happen gradually. So your conclusion, this is continuous and differentiable. What does the mean value theorem say? Well, if you have a function that's continuous and differentiable, then the slope of the secant line there must be equal to the slope of the tangent line at some point. There's got to be a point where the slope of that tangent line is parallel to the slope of the secant line. And what is the slope of the tangent line? That's the instantaneous rate of change, or the velocity of the car at that point. Okay? So we're going to find the average rate of change, and we are guaranteed that that car had that instantaneous rate of change. In other words, this is a graph of x of t. The mean value theorem says the derivative at some point t must be equal to I'm going to change this to hours by dividing by 60. This is the slope of the secant line, the average rate of change. And we're told by the mean value theorem that the instantaneous must equal the average at some point. Let's continue going here. If you were to work this out, this would be, the final position would be 30 minus 0 over 28 over 60 minus 0. And that is approximately, I have this answer, 64.3 miles per hour. So since the slope of that's 64.3, there must have been a time where the car was traveling instantaneously at a speed of 64.3, guaranteed by the mean value theorem. Therefore, you got a ticket because of the mean value theorem. Sad.